Hello, everyone. I hope you had a nice break, spring break. We're going to go over. We're going to go over section 17.1. The objective is to calculate the average rate of a chemical reaction. Okay, from experimental data, and then the rate of a chemical reaction to collisions. So we're going to figure out the relationship between collisions and the rate of a reaction. Okay, let's see.
Reaction rate. The change in concentration of a reactant or product per unit time, generally calculated and expressed in moles per liter per second.
Okay, so it's a change in concentration, the change in quantities over change in time. And I'm going to go over that. And the time is usually seconds, but sometimes it can be minutes. You just have to pay attention to what they're asking for and what's given to you. So if it's a change in reactant, the reactant is going to decrease over time, okay? And the product is going to increase over time. So you have to pay attention, close attention to the sign.
Collision theory states that atoms, ions, and molecules must collide in order to react.
Okay, not only do they have to collide, but they really have to collide at the right orientation and the right amount of energy. Think of this as a football player. In order to get to tackle someone, you have to have the right amount. You have to be same amount, just as strong as the other person, and you have to get him at the right angle. Think of Muhammad Ali when he gets the knockdown. It has to be the right amount of energy at the right amount of angle, or the guy will not go down. Something to think about. All right, so here the right reaction, if they collide at the right orientation and the right amount of energy, then you get to the product. If you don't, then let's say oxygen and hydrogen are supposed to or colliding, but they did not collide at the right orientation or the right amount of energy, then they'll go on their separate ways, and that's ineffective collision. Activation.
Activated complex. A short lived, unstable arrangement of atoms that can break apart and reform the reactants, or can form products. Also sometimes referred to as the transition state.
Okay, this transition state or activated complex is very, very brief. And that's where, if it's the right orientation, right amount of energy, then the old bonds are breaking and new bonds are being formed. And this gives you just examples of right orientation, insufficient or sufficient amount of energy.
Activation energy. The minimum amount of energy required by reacting particles in order to form the activated complex and lead to a reaction.
Okay, right amount of energy is that energy, this right here, the barrier that you have to get over, and in order to get over, you have to have the right amount of energy. If you don't have enough energy, you won't be able to go over on top to the top of the hill. Okay, so if you do, then at this point, this is the activated complex where bonds are being broken and new ones are being formed. All right. So the rate of the reaction, or the average rate of reaction, we said it's the change in quantities over change in time. And the quantity is, remember we talked about molarity, capital M, which is moles per liters, over change in time. Moles per liter per second. This is the actual unit. So if they're giving you in minutes, you have to convert it to seconds. All right. And exo, right. So we had a better picture here. Let's see. Oh yeah, right here. Now, from the reactant, there's more. This is an exo because the product has more energy or released by the reaction. Energy is being released, that's exo. And this one, oops, sorry. This one, energy is being absorbed because the reactant now has a higher energy, so somehow they absorbed energy during the reaction. So that's endothermic. All right, so this is the one I'm going to talk about. Over time, in seconds, the concentration, I apologize, it's a little blurry, but I had to stretch it so it fits my screen. Over time, the reactant decreases and the product increases. Think of it as you're mixing chocolate with milk. Over time, the chocolate is going to disappear as chocolate milk appears, increases. So you want to think of this as disappearance. The reactant will disappear as the product appear. And when it appears, it's positive. When it disappears, it's negative. Okay, and the bracket, we said the brackets represent the concentration, which is moles per liter. All right, so let's talk about this. Let's talk about how to analyze a graph. So let's say at any given time, and a given concentration, we want to find the average rate. So we're going to draw our famous triangle and then draw a line across. And now this is approximately, oh, I'm sorry, this is not 4, this is 0.4. Okay, we'll just go along with it because I already put it down, but it's 0.4. I didn't see that. So let's pretend this is 4 and this is 1.9. So you take the difference between the two. 4.2 minus 1.9, which is 2.3. And in the time, it's about 2.5 seconds, starting 2.5 seconds to 7.5. So you take the difference of the two. Final minus initial. Final minus initial. And then the next step, you have to divide them. So you divide 2.3 by 5, you get 0.46. Now, of course, because this is 0.4, which I didn't pay attention to, I'm sorry, it would be 0.046. Now, the curve I chose was the blue one. The blue one is increasing and the sign will be positive. So when it increases, the sign is positive. When it decreases, the sign is negative. Okay? With that, let's practice. Okay? Let's find an example. It says calculate the average reaction rate expressed in moles consumed per liter second. Okay, hydrogen. They're saying hydrogen, so that's hydrogen and the time. Now, 0 is initial, 0.03 is initial, 4 is final time, 0.02 is final concentration of hydrogen. Excuse me. I have a little cold. So now change in concentration over change in time. So final 0.02 minus 0.03 divided by 4 minus 0. So negative. So the curve will be the one that is decreasing. And you divide. And that's what you get. 0.0025. Excuse me. Now another example, you can pause at any time. I just want to get through to 2 more slides. Calculate the average reaction rate expressed in chlorine. So chlorine and the time. Final minus initial, final minus initial. So change in chlorine over change in time. 0.04 minus 0.05 divided by 4 divided minus 0, and then divide. Okay, and if it's negative, the curve is going to be decreasing over time. Or you would know that this is the reactant because it's decreasing over time. So sometimes the questions would say, is this a reactant or product, or is this increasing or decreasing based on the answer. All right, last, calculate the average reaction rate expressed in moles of HCl over time. So again, 0.02 is final, 0 is initial, 4 is final, 0 initial. So you just subtract and then divide. It's positive, so the rate, this is the rate of the product. It's increasing as it appears over time. All right, I hope that helped. If you need any further help, let me know, please. Okay, take care.